On May 20th, 2024, Microsoft introduced a new class of computer and quietly changed what a personal computer was expected to remember. The machine was called a Copilot Plus PC. Its defining feature was not its screen, battery, or processor speed, but an integrated neural engine. Then came Recall, a system designed to capture searchable snapshots of activity, turning passing moments on a screen into persistent machine memory. Within weeks, security researchers and privacy advocates were asking the question the launch presentation avoided: who controls that memory? Microsoft delayed the rollout, rebuilt protections, made Recall opt-in, tying access to encryption and Windows Hello. But the architecture survived. By 2026, the AI PC was no longer a speculative product category. Neural processing units had become standard silicon inside mainstream laptops. The computer had gained a new organ, optimized to classify voices, faces, images, gestures, documents, and behavior without exhausting the battery. And for the first time, escaping an operating system could also mean reclaiming a physical accelerator embedded inside the processor package. This is where the argument becomes uncomfortable, because an NPU is not literally a surveillance device. It has no secret antenna, no independent internet connection, and no mystical ability to watch a user by itself. It is an inference accelerator waiting for software, firmware, memory, and permission. That distinction matters. Calling every NPU a spy chip would be technically false, and technical exaggeration only protects the companies that deserve scrutiny. The real danger is more subtle. Local artificial intelligence makes continuous analysis cheap, quiet, responsive, and commercially irresistible. Before dedicated neural hardware, persistent interpretation of a desktop was expensive. It consumed CPU cycles, drained batteries, generated heat, or required cloud uploads that users and network monitors could detect. An NPU removes those frictions and makes always available inference feel like a basic operating system service. That is why the phrase, "it stays on your device," cannot end the privacy debate. Local processing reduces exposure to a remote server, which is valuable, but it also enables far more information to be captured, classified, indexed, and retained than would otherwise be practical. A locked archive can still become a target. A local database can still be queried by malware, exposed by a vulnerability, inherited by a future software update, or accessed after account compromise. Privacy depends on authority and retention, not merely the physical location of computation. Microsoft's current documentation says Recall snapshots are saved and analyzed locally, are not sent to Microsoft, and require explicit user action to share. Those are meaningful safeguards. Recall also requires encryption and enhanced Windows Hello protection, and managed systems can disable the feature through policy. But the larger design direction remains visible. The operating system increasingly mediates the screen through machine vision, offers contextual actions based on visible content, and makes neural inference part of the desktop's default vocabulary. One controversial feature can be revised while the platform strategy continues. Click to Do illustrates that strategy. When activated, it analyzes a screenshot and identifies text or images that can be acted upon. Microsoft says the analysis remains local, although selected content can leave the machine when a user chooses an online provider such as web search. Again, the issue is not that every pixel is secretly transmitted. The issue is that an operating system vendor is establishing a normalized pipeline from human activity to screen capture, to model inference, to suggested action. Once that pipeline exists, policy determines how it evolves. Policy is not hardware. A checkbox can be renamed, a default can change, a feature can be separated into services that remain installed even when its visible interface disappears. An enterprise setting can protect one edition, while a consumer edition follows a different commercial incentive. The NPU makes this transition durable because it changes the economics beneath the interface. A 40 trillion operation per second accelerator can run supported models efficiently while the main processor remains available. Analysis that once looked intrusive or wasteful can now be marketed as ambient convenience. Intel integrates an NPU into Core Ultra systems. AMD integrates XDNA accelerators into Ryzen AI platforms. Qualcomm's Snapdragon X systems include dedicated neural processing as a central selling point. Different architectures compete on performance, yet all point toward the same operating assumption. AI should always be nearby. On Windows, users negotiate with that assumption primarily through settings supplied by the vendor. They can disable a feature, remove permissions, apply policy where supported, and trust that the documented boundary matches the executing system. The vendor still defines the menus, services, update channel, and supported escape routes. Linux changes the negotiation because device access is exposed as a stack rather than presented as a promise. The hardware is enumerated, a kernel driver binds to it, firmware may be loaded, a device node appears, permissions are assigned, and user space runtimes submit workloads through documented interfaces. Break any necessary link in that chain and ordinary applications lose the accelerator. The NPU remains physically present, but physical presence is not the same as operational authority. Silicon without a bound driver and accessible interface is not a useful background inference service for the desktop. This is the real Linux advantage. It does not magically purify proprietary hardware, and it cannot reveal every instruction inside vendor firmware. It gives the machine owner multiple enforceable points where access can be denied, observed, narrowed, or removed independently of an application's preferences. Consider an Intel AI laptop. The kernel-side NPU driver is commonly identified as Intel VPU, while the active device can appear under the accelerator framework as a node, such as DOS-Dev Excel 0. User space components then use that interface to compile and submit neural workloads. On newer AMD Ryzen AI systems, the upstream driver is AMD XDNA. Kernel documentation describes an integrated accelerator with compute tiles, local memory, firmware-managed components, DMA engines, and hardware isolation between workload contexts. That description is useful precisely because it exposes where control and risk actually live. DMA is a critical word. An accelerator needs to exchange data with host memory, and any DMA-capable device expands the security conversation beyond a simple application process. The Linux kernel's IOMU infrastructure exists to restrict which memory mappings a device can reach and to separate devices into enforceable domains. The first countermeasure is therefore not a custom kernel module. Writing new privileged code should never be the opening move when established kernel controls already exist. The first move is inventory. Identify the exact device, driver, firmware, node, permissions, and processes involved on the specific machine. Commands such as lspci with kernel driver details can reveal a PCI accelerator. lsmod can show whether intel.vpu or AMD XDNA is loaded. The kernel log can reveal firmware initialization, while the .dev Excel directory shows whether an interface was created for user space. That inspection replaces fear with evidence. If no NPU driver is loaded and no accelerator node exists, a desktop application cannot simply issue normal inference jobs to that device. If the driver is present, the next question becomes which accounts and services are allowed to open it. The strongest clean disable is often found before Linux boots. Some manufacturers expose an NPU, AI accelerator, or neural processing toggle in UEFI setup. Disabling the device there can prevent the operating system from enumerating it, eliminating an entire driver and access path at the platform boundary. Not every vendor provides that switch. Firmware menus vary by model, updates can rename options, and some thin laptops hide controls that business systems expose. That inconsistency is itself revealing. Ownership is constrained when a purchased component cannot be independently disabled through the machine's own firmware interface. When firmware offers no switch, Linux can refuse the driver. A module blacklist can stop normal automatic loading of Intel, VPU, or AMD XDNA. On distributions that package these drivers as loadable modules, an administrator can place the relevant rule under modprobe configuration and rebuild the early boot image. The early boot image matters because simply unloading a module after login is weaker. A driver may already have initialized firmware, created a device node, or served a process. Preventing activation during boot closes the window instead of attempting to clean up after the accelerator has entered service. A blacklist alone is not always absolute. Another module can request a dependency, an administrator can load a blacklisted module explicitly, or a distribution can compile the driver directly into its kernel. Strong configurations add an install rule that causes a load attempt to fail and verify the result after every reboot. If the driver is built into the kernel, modprobe cannot remove it because there is no separate module to unload. The owner then moves one layer deeper. Use an appropriate kernel command line control if the driver provides one, or build a kernel with that accelerator option disabled. For AMD's upstream implementation, the relevant configuration symbol controls DRM accelerator support for the XDNA device. For Intel, the NPU support can likewise be modularized or omitted. A custom kernel is not mystical counter-surveillance code. It is a smaller statement of which hardware the operating system agrees to operate. This is where reproducible configuration becomes more important than heroic hacking. The kernel config should be stored, versioned, compared after upgrades, and rebuilt through a repeatable process. Otherwise, the next distribution update may reinstall a generic kernel and silently restore the driver path. There is also a runtime option. Linux exposes driver binding through SysFs for many PCI devices. Once the NPU's exact PCI address and current driver are confirmed, the device can be unbound, causing the kernel driver to release it and removing the ordinary interface used by applications. Unbinding is useful for testing and emergency containment, but it is not equivalent to power removal. Kernel documentation warns that some initialization may not be fully reversed, and a device can potentially be rebound. A reboot also restores the default unless a persistent boot policy repeats the action. The PCI subsystem can remove a device from the kernel's active list until the next rescan or reboot. That is a stronger operational disappearance, yet it still does not guarantee the component is electrically off. Precision matters. Invisibility to Linux, driver detachment, reset, and physical power isolation are different states. A defensive setup should state exactly which state it achieves. The NPU has no bound host driver and no user space device node is verifiable. The NPU is completely dead may be impossible to prove without platform documentation, power measurements, and firmware control unavailable to the owner. This honesty does not weaken the counteroffensive. It makes it real. Security is built from claims that can be tested after updates, suspend cycles, firmware changes, and reboots. A dramatic label without a measurable condition is only another vendor promise wearing different colors. Even when the owner chooses to keep the NPU available, Linux can reduce its audience. Access to accelerator device nodes is normally governed by Unix ownership, groups, and permissions. If an account is not authorized to open the node, its applications cannot submit ordinary workloads through that interface. This creates a middle position between total activation and total removal. A dedicated local inference account can receive access while browsers, document readers, communication tools, and the everyday desktop session remain outside the permitted group. Neural capability becomes compartmentalized instead of ambient. System service hardening can narrow access further. Device policy can deny physical device access to a service, while file system restrictions, capability removal, syscall filtering, and isolated temporary directories reduce surrounding privileges. The NPU should be treated like a sensitive peripheral, not like harmless background arithmetic. Mandatory access control systems, such as CLinux or AppArmor, can add rules around the user space runtime and the files it may read. That matters because restricting the accelerator is only half the problem. A perfectly contained model can still process private documents if its launching application can open them. The data path begins at sensors and files, not at tensor execution. A camera captures the face, a microphone captures speech, a compositor displays messages, and an application reads documents. The NPU transforms inputs it receives. It does not need to own the sensor to participate in surveillance. Therefore, disabling only the NPU cannot blind the machine. The same inference can fall back to a GPU, CPU, remote server, browser API, or separate coprocessor. A serious strategy controls collection, computation, storage, and transmission as distinct layers, because removing one accelerator closes only one path. Camera and microphone devices should be physically shuttered or disconnected when possible, and their kernel drivers or permissions should be reviewed separately. Screen capture permissions under modern Linux desktops should be granted narrowly through portals rather than assumed to be a universal background entitlement. Wayland helps by changing the old desktop capture model. Applications generally cannot scrape every window merely because they share a graphical session. Screen sharing is mediated through the compositor and desktop portals. That does not eliminate trusted component risk, but it narrows what ordinary applications can silently observe. The storage layer must also be addressed. Full disk encryption protects data when the machine is powered off, but it does not protect an unlocked session from authorized processes or malware. Sensitive archives need retention limits, application isolation, and clear deletion behavior, not just encrypted sectors. The network layer provides the final reality check. An NPU has no reason to speak TCP or open a cloud connection itself. A host process does that. Outbound firewall rules, DNS visibility, per application network controls, and packet capture can reveal whether an AI feature remains local or contacts external infrastructure. This is one reason Linux can convert marketing language into an experiment. Put the relevant application inside a network namespace with no route, run the workload, and observe what succeeds. If a supposedly local feature stops functioning, the dependency is exposed without waiting for a privacy statement to be revised. Conversely, a local model can remain useful inside that sealed environment. Open runtimes can execute speech recognition, image classification, or language models on CPU, GPU, or an intentionally enabled NPU without sending source material away. Neural computation and corporate telemetry are not inseparable technologies. The fight is over governance. Who selects the model? Who can inspect the runtime? Which files can it open? What is retained? Which network destinations exist? Can the user remove the feature completely without breaking the operating system or violating on an artificial support boundary? On a proprietary AI PC, these questions are answered inside a product roadmap. On Linux, they can be encoded as boot parameters, kernel configuration, UDEF permissions, service sandboxes, access control policies, firewall rules, and reproducible tests. The result is not automatic privacy, but owner-defined enforcement. The verification phase begins after the controls are applied. Reboot the machine, then repeat the inventory. The target driver should be absent, the accelerator node should not exist, and the kernel log should not show a successful firmware boot or a late module load. On Intel systems where the driver is active, CISCs can expose current, frequency, busy time, and memory utilization. Those counters help demonstrate actual job submission. An idle reading alone proves little, but changes correlated with an application can identify when the accelerator is being used. Device files should be checked for open handles. A process listing or file descriptor inspection can identify which service has opened an accelerator node. Audit rules can record future access attempts, providing a durable answer when an application unexpectedly activates the hardware after an update. Package inventories matter as well. Kernel control blocks the hardware path, but vendor user space runtimes, model compilers, firmware packages, and AI desktop services may remain installed. Removing unneeded components reduces code, background activation, and the chance that a future update restores an integration layer. Secure boot complicates custom kernels but does not eliminate owner control. A user can sign a personally built kernel with a personally managed key on supported systems. The important distinction is whose trust policy the machine enforces, and whether the owner can enroll or remove keys without surrendering boot integrity. Firmware is the hardest boundary. Many NPUs depend on binary firmware loaded by the host, and some include internal microcontrollers whose executing code is not fully inspectable. Linux can deny loading and binding, but it cannot transform a closed firmware blob into transparent software through willpower. That limitation is why the strongest purchasing decision happens before installation. Buyers can favor systems with documented Linux support, visible firmware toggles, published interfaces, upstream drivers, replaceable peripherals, and a UEFI that preserves owner key management. Repairability should include computational consent, not only screws and batteries. There's another boundary that must not be confused with the NPU: platform management hardware. Intel's management engine and AMD's platform security processor serve different boot, security, and management functions. Disabling the neural driver does not disable those subsystems, and claiming otherwise creates a dangerous blind spot. Likewise, a laptop may contain image signal processors, sensor hubs, presence detectors, audio DSPs, and embedded controllers capable of limited autonomous work. AI hardware is not one chip. A complete threat model maps every device that can receive sensitive input, access memory, wake the system, or influence software. Linux does not abolish that federation. It exposes more of the treaties. Drivers reveal device identifiers. Logs reveal initialization. SysFs reveals bindings. IOMU groups reveal isolation boundaries. And source code reveals the kernel-side control flow. Visibility becomes the foundation for refusal. Custom kernel modules can play a role when vendor hardware lacks a clean disable control. A small defensive driver could claim a PCI identifier and intentionally expose no workload interface, preventing the normal driver from binding. But privileged custom code introduces maintenance and security obligations of its own. Such a module must match hardware carefully, handle power states, survive, suspend and resume, avoid unsafe register access, and keep pace with kernel interfaces. A mistake inside kernel space can crash the system or weaken isolation. The simpler supported mechanism is usually the more trustworthy mechanism. That is why a layered order matters. Firmware disable first, kernel omission or boot time refusal second, persistent driver blocking third, device permission denial fourth, and runtime unbinding as a temporary control. Each layer should be tested independently and documented for the specific laptop. The setup should also fail closed. If a distribution upgrade introduces a renamed driver or new device identifier, the verification process should detect the restored node before the daily session begins. A boot time assertion can stop or alert when the accelerator unexpectedly becomes available. The same principle applies to application updates. A browser that gains a local AI feature should not automatically inherit access to every personal file, microphone, screen, accelerator, and network destination. Sandboxing should make each permission explicit, narrow, revocable, and observable. Containers are useful but not magical. A container sharing the host kernel can still receive devices deliberately passed into it, and a privileged container can collapse boundaries. Virtual machines with strict device assignment create stronger separation, though usability and hardware grouping may limit what can be isolated. For many users, the practical sovereign configuration is simpler. No NPU driver, no accelerator device node, Wayland screen mediation, camera shutter closed, microphone permission restricted, full disk encryption enabled, and outbound connections limited for applications handling private material. That configuration will not stop every form of tracking. Websites can fingerprint browsers, accounts can correlate activity, cloud documents can be analyzed remotely, phones can collect nearby signals. Disabling one local accelerator cannot repair an ecosystem built around identity, advertising, and behavioral prediction. But it changes an important default. It prevents the operating system and ordinary local applications from treating a dedicated neural engine as an unquestioned shared resource. It turns an invisible capability into a component that must cross an owner-controlled boundary before it can operate. Some will argue that this sacrifices useful features. They are right. Background removal, live captions, noise suppression, local transcription, accessibility tools, and private on-device models can benefit from efficient neural hardware. An NPU can reduce cloud dependence and improve privacy when the user governs it. The goal is not technological purity, it is reversible consent. A trustworthy AI computer is not one that promises benevolent inference. It is one where the owner can enable a model for a defined task, inspect its access, then disable the entire path without negotiation. This is where Linux offers something larger than an alternative desktop. It supplies a constitutional layer between software ambition and physical machinery. Applications can request capabilities, but the kernel, device policy, and owner determine whether those requests become real access. The Linux model is imperfect and often inconvenient. Hardware support may arrive late. Firmware may remain closed. Laptop vendors may omit switches. Distributions may load broad defaults to maximize compatibility. Sovereignty is not delivered by installing a penguin logo. It is constructed through deliberate configuration. That construction begins with a threat model, not a command copied from a forum. A journalist protecting sources, a company guarding prototypes, a family avoiding behavioral archives, and a researcher running confidential data face different risks and should choose different levels of isolation. The phrase hardware-level neural surveillance should therefore be understood precisely. The hardware does not create the surveillance objective. It lowers the cost of continuous interpretation and embeds the capability so deeply that software vendors can present observation as a natural property of modern computing. Once interpretation becomes cheap, incentives fill the vacuum. Operating systems can summarize activity, rank attention, infer intent, anticipate actions, and build searchable histories. Even when every individual feature launches with safeguards, the combined architecture moves the computer from a passive tool toward an active observer. An observer that works locally may be safer than one streaming raw data to the cloud. It can still alter the balance of power inside the machine. The crucial question is whether observation begins only after an informed command, or whether the user must continually defend against an expanding default. Linux lets the owner answer at the device boundary. No bound driver means no conventional workload submission. No device node means no ordinary user space handle. No permission means no authorized open. No network route means no remote provider. Each statement is narrow, testable, and enforceable. Together, those statements form something corporate privacy dashboards rarely provide: an independently verifiable refusal. The user is no longer asking a feature to respect a preference. The system is structurally unable to use the accelerator through the blocked path until the owner changes the configuration. That difference will become more valuable as neural units grow faster and more integrated. Today, they accelerate selected models. Tomorrow, they may support richer context across applications, persistent agents, multimodal search, and interfaces that continuously interpret speech, vision, location, and routine. The time to establish owner control is before those capabilities become inseparable from login, updates, productivity software, and hardware certification. Once refusal breaks essential functions, a nominal off switch is no longer meaningful. Dependency can become a form of coercion without any dramatic mandate. Escaping the AI PC does not require smashing the laptop or retreating from machine learning. It requires rejecting the claim that purchased silicon must serve the operating system vendor's preferred future. The accelerator can remain dark, become compartmentalized, or run only models chosen by its owner. The decisive act is not installing Linux by itself. It is tracing the entire neural path from sensor to process, from process to driver, from driver to firmware, from firmware to memory, and from stored result to network. Every link must justify its existence. When a link cannot be justified, Linux provides ways to cut it. When it cannot be cut, Linux provides evidence that the boundary lies in firmware or hardware, guiding the next purchasing decision instead of disguising the limitation behind a polished settings page. This is how the silicon is reclaimed, not through mythology, but through enumeration, refusal, isolation, verification, and repeatability. The NPU stops being an invisible entitlement of the platform and becomes what every component inside a personal computer should be, a resource subordinate to its owner. The neural eyes are not blinded because the machine forgets how to calculate. They are blinded because no untrusted observer is permitted to deliver the images, open the device, retain the inference, or transmit the result. Control replaces assurance at every layer. The future of personal computing will not be decided only by how intelligent machines become. It will be decided by whether intelligence remains a capability we summon or becomes an environment that silently interprets us whenever power reaches the motherboard. Linux cannot guarantee freedom through branding, and hardware cannot guarantee surveillance through existence. But an owner-controlled kernel can draw a line in the silicon, enforce it at boot, verify it after updates, and refuse to let convenience erase consent. That line is the real escape route from the AI PC, a computer that may contain neural machinery, yet possesses no standing permission to observe, classify, remember, or report the life unfolding in front of it.